Hello, in this video we're going to explore how to calculate the entropy change for supercooled water and determine if, as we know is the case, it's a spontaneous process at -5 degrees. So I don't like this, so I'm going to stop and pause. Hello, in this video we're going to learn how to calculate the entropy change for supercooled water. We know that water, liquid water, is not stable at -5 degrees. The normal freezing point, of course, is 0 degrees. But if we cool it very slowly and carefully, we can actually get liquid water to exist at -5 degrees because crystallization can be difficult in a pure environment without any kind of contamination or with the waters contained within a vessel that has smooth surfaces. So it is possible to generate water at temperatures below -5 degrees, but any slight disturbance, and you can find all kinds of videos on the internet that show this, and you can even try this at home, any slight disturbance will cause it to crystallize very rapidly. So we know it's a spontaneous process. We know it's going to happen under those circumstances, and that means, based on our understanding of the second law, that the entropy change for the universe should be greater than 0 for this process. But how can we calculate that? So we're going to set this up. Now, the thing to remember is that when we talk about delta S, and the definition of delta S is that it requires that we use a reversible path to determine dq, which is the heat transferred involved in a particular process. And clearly at -5 degrees, this is not a reversible process. It is a reversible process, however, at 0 degrees. At the transition temperature, we have an equilibrium between the liquid and the solid, and that makes it reversible. So we need a reversible path. So what's our reversible path going to be? Well, what we're going to do is we're going to reversibly heat the process to 0 degrees. So we'll take the liquid, we'll heat it to 0 degrees, then we'll allow it to freeze at 0 degrees. And that is reversible because it is at the transition temperature, and that is the equilibrium situation. And then we're going to allow it to cool reversibly. So we're allowing the ice to cool reversibly. So we've got this three-step reversible process. Imaginary though it may be, it's going to allow us to do the calculation for the entropy change at -5 degrees. We just need to calculate the entropy change for each of these three steps. We'll call them steps 1, 2, and 3. And the total entropy change for the system is just the sum of step 1, step 2, and step 3. All right, so that's what we need to do. We need to calculate then the entropy change for each of these three, and that will give us a total entropy change for the system. Now, we'll come back to this later, but we are talking about the system, and I think you can guess what the sign of this entropy change is going to be based on the idea that two things here. First of all, when we go back to probably the first introduction you had to entropy, you associated with an order-disorder kind of thing, and more disorder meant a higher entropy. If we're going from a liquid to solid, that would seem to indicate we're going to a more ordered system, so we would expect delta S to be less than 0. Based on that, the other thing is that based on the definition of entropy, the thermodynamic definition of entropy, which is based on heat, we know that freezing is an exothermic process. If freezing is an exothermic process, then that also would indicate that delta S is less than 0. So we're going to check that out to make sure that's the case, and then we're going to ask the question, okay, what does that say about the second law? Why is it spontaneous if we're calculating a delta S value less than 0? So we'll get to that later, but let's just go through our steps here, and we're going to go through how we're going to figure this out, and then we'll run through the calculation itself. So step one. All right, step one involves heating the liquid. So how do I calculate the entropy change for heating something? All right, so we'll go back to our definition here for the reversible process. Okay, and we have to ask, okay, what's dq going to be equal to when we have a heating process? Well, so you probably know that if you go way back to simple heat capacity, definitions of heat capacity and thermodynamics, that dq is going to be equal to the heat capacity, and we're going to talk about the constant pressure heat capacity because we're carrying this out under conditions of constant pressure. So it's just equal to Cp dt. No doubt you've done some calorimetry experiments in the past where you measured a temperature change and used the heat capacity to figure out how much heat was absorbed or generated in a particular process. And you use this equation as indicated here. Normally, in most simple experiments, we assume that the heat capacity is independent of temperature. So that means that under those circumstances, if the heat capacity is independent of temperature and we do an integration, it's a pretty straightforward calculation to calculate Q, the heat associated with a particular process. One has to be careful about that assumption because if the temperature range is large enough, then we can't assume that heat capacity is independent of temperature. But that's something for another day. We're going to focus on entropy here. And so what we're going to do is we're going to take our definition of entropy and plug it into this equation for entropy. And that means we're going to do Cp dt over T. And now we'll integrate both sides of that equation. And when we do the integration, we'll just say we're integrating from T1 to T2. All right, those are our temperature changes. So it's going to be delta S. Integrating ds is just going to be delta S. And so, again, we're going to assume the heat capacity is independent of temperature, so we bring that side outside the integral. But then we've got dt over T. And when we do that integration, it's like 1 over x dx. So this is just going to be the natural log of T2 over T1. All right, so that's going to be how we're going to calculate that in step one. So let's take a look at that. And I'm going to use Wolfram Mathematica to just run through this calculation, and which can also work in the Wolfram Cloud. It's done the same way to do that. So I'm going to pause here for a second, and I'm going to bring up that program. Okay, so I'm going to use Mathematica here, the desktop version, but this will work in the Wolfram Cloud as well. So the first thing we're doing is we're going to calculate the entropy change for the heating of liquid water from -5 degrees to 0 degrees Celsius. And we just showed that the relevant equation here is this delta S equal to Cp natural log of T2 over T1. So what we're going to need is the heat capacity of liquid water, which we can look up. It does turn out that Wolfram does have embedded in it thermodynamic data that would allow us to access it, but it does have some weird unit properties. So I'm just going to go ahead and do this myself with the quantity function. It's a good idea to get used to using quantities, the quantity function for units. It's easy enough to remember. So if we look it up here, I'm going to call it CPL. I'm just going to say equals, and quantity allows me to enter 75.3768 and that's the number. And now I'm just going to enter the units for this. There are a number of ways we can enter it. I'm going to do it the long way, but you can actually use the abbreviations if you want. So joules, so I start to type it, and you see that what Wolfram is doing right away is trying to guess what I'm doing. So yes, joules is what I want, so I'm going to enter. Divide it by, and I'm going to enter kelvins, and there it's guessed, so enter, times moles, and we're enclosing these in quotation marks. Let me slide this over a little bit so I don't run out of space. All right, moles, enter, close bracket, shift enter. Oops, I forgot parentheses here. There we go. And that's what I've got. So there is my value for the heat capacity for liquid water. And I'm assuming it's independent of temperature when we do this. So now I'm going to go down here and use the equation, Cp times the natural log of T2 over T1. So what we're going to do is I'm going to type in delta S, and we can learn the Greek alphabet. You don't need to use the Greek characters if you don't want to. There are shortcut keys that allow you to do it, however. So if I start with escape, and then I hit Shift D, and then escape again, right, you see I've got delta, all right, because capital D is the counterpart to delta. And so now I'm going to enter S, and since this is step 1, I'm just going to enter a 1 here to distinguish this from the others, equal to, and it's the heat capacity, which is, I entered as CPL. And again, just a reminder here, I just get in the habit of every number that I'm entering in my Wolfram notebook to assign it to a variable. That way it's just, even if I'm only using it once, it's just easy to label things. And if I'm using it more than once, it means I don't have to type the number in every time. I can just use the variable name that I've assigned. So it's going to be CPL times. And here's the thing that's kind of confusing about Wolfram. I'm not sure why it's set up this way, but for natural logs, the function, Wolfram function is log, not ln. And this is going to be confusing, I think, at first when you first start doing this, because you will probably no doubt think of log as base 10 common logarithm, because that's pretty much probably how you've done it in the past. But log, just log for Wolfram is equivalent to natural log. If you actually look down here in this grouping, log 10 comes up as one of the possibilities, and that's what you'd use if you wanted to use the common logs. So, and then bracket, square bracket. And again, remember that Wolfram functions all start with a capital letter, and the arguments of the Wolfram functions are enclosed within square brackets, not parentheses. And so now I'm going to do temperature, which I haven't entered yet, and I can go ahead and do this. It's going from 273 to 268, but I think what I'm going to go ahead and do is actually enter the temperatures with variable names, so that way I only have to type it once. And so here's how I'm going to do this. So there are two ways I can do this. I can use the Wolfram function quantity. So I'm just going to say T1 equals quantity. I don't think that's entering it as a function there. Okay, let's try again. T1, there we go, equals a quantity. And I'm going to enter 268, and then parentheses, kelvins. Now, actually, if you just enter the K, more than likely Wolfram will figure it out. Let's try it and see. So you have to type kelvins or hit return. And it does. I mean, Wolfram sometimes will figure out the abbreviations if you use it, sometimes not. So there's quantity. The other way to do it, of course, is the freeform way. And let's do T2. Let's do T2 that way. Equals, and then I can do a control equals. So now I'm in my freeform mode. You get that little orange equal sign, and I'm going to type 273 kelvins. In my mind, for something like this, it's just as easy to do the quantity function, because the other advantage of the quantity function is you don't need access to the web to do it. With the freeform mode, it's going to go to the web to look for the equivalents. And then again, shift enter, and now I've got my two temperatures. So now I'm back down here, and it's going to be T2, the higher temperature, divided by the lower temperature in the case of the heating. And boom. All right, so that's That's what I've got. You know, this is positive, as you would expect, because we're heating something. We're putting heat into it. That's going to increase the entropy. That's going to increase the disorder. So that should make sense to you under those circumstances. Okay, so now we need to move on to the second step, which is freezing. So I'm going to pause here for a bit, and we'll come back to that. Okay, we're back. All right, now we're getting ready to do our calculation for step 2, which, let's just scroll back up to here to our process. Step 2 is the freezing of our ice at 0 degrees Celsius, which is a reversible process. All right, so scrolling back down here, how do we do that? Well, again, just going back to our definition, ds is equal to dq over t. In this case, the freezing process is in fact reversible, so we can just use the heat transfer during freezing, and that's just the process involving the enthalpy change for that particular reaction. So delta H of fusion is the enthalpy of fusion associated with the freezing process. The one thing to keep in mind for this is that we have to include the negative sign because the values of the enthalpy of fusion that are tabulated are positive values. Even though fusion sounds like it's freezing, then the freezing process is not. All right, going from a less condensed phase to a more condensed phase is always going to release heat, and so it is going to be exothermic. And so the values tabulated are positive, but we need to make sure we're using the exothermic value in this particular calculation. So I just need then to put a negative sign in front of that, so that would be the case. And so this means in this case we're going to need to look up the enthalpy of fusion, all right, when we do that. All right, so now what I'm ready to do is calculate delta S for the freezing process, where we're talking about at 0 degrees Celsius. It's being reversible. It's an equilibrium. So again, basically what I need to do is get the enthalpy of fusion, all right, which again I can look up. So the enthalpy of fusion here, if we go back to looking it up, is 6,008 joules per mole. So I'm going to go ahead and do that. So I'm going to enter delta H. So escape, shift D, escape, H. And again, I'm going to use the quantity function. 6,008. And I could enter it with the freeform method as well. Joules per mole. And again, you'll notice when I'm entering the quantity function that the units are in quotation marks. That's important to remember. Close bracket, shift enter, and there's my value for delta H. All right. So for step 2, which is the freezing process, delta S is just equal to delta H, negative delta H of fusion over T. Again, remember it's an exothermic process, so we're going to do this, escape, shift D, escape, S2 for step 2 is equal to delta H, escape, divided by, in this case, 273 Kelvin, which I've labeled as T2. You can see the advantage of assigning variables. I only need to type the number in once, and it'll work, and then shift enter. And so there's my value. Now here's something that's interesting, and that is what Wolfram Alpha will always try to do is give you the answer that is most precise and most exact. If the answer is a rational number, that means if it can be expressed as a fraction, it will express it that way because that would be the exact result. And that way you get the more precise answer. If you want to know what the numerical value is, you see we've got a suggestion bar that pops out up down here in the bottom. If I just hit numerical value, it will give us the value for that. Oh, and I did forget something. I forgot that this is exothermic, so it should be negative. So let me redo that. And then I'm going to redo this. All right, so it's negative. All right. So, and again, that's an easy thing to forget. Obviously, I forgot it. This is an exothermic process. Heat is released in this process. It is freezing. It's going from liquid to solid, so you should get a negative entropy. And that's something you should get in the habit every time you do a calculation to really look at your answer to see if the answer makes sense. And one, sometimes the easiest, sometimes the magnitude maybe not so easy to assess, but signs are easy to assess. We know we should get a negative result here, and if I don't get a negative result, I need to go back and take a look and see where I might have missed the sign someplace, which is exactly what I did in this particular circumstance. So now I've got the negative value here for freezing. There's a negative entropy change because things are becoming more ordered because it's an exothermic process. So now I'm ready to move on to step 3. So we'll pause here and come back. Okay, so we're in step 3 now, the last step of our 3-step process to calculate the entropy change for the freezing of supercooled water. And now we're just at the point where we have gone through step 1, where we've heated the liquid water to 0 degrees, step 2, frozen the liquid water to ice, and now we're going to take that ice and cool it back down to -5 degrees. So we need to calculate delta S for that process. And again, it is a temperature change process. So the equation we're going to use here is going to be the same as the equation that we used for step 1, except it's the heat capacity of ice that we have to be using instead of the heat capacity of the liquid. So we're going to need to look that up. And then it's going to be T1, which the way we have done the calculation, T1 was equal to 268 Kelvin and T2 is 273. So we're going from 273. Let me just write this out. Okay, so we're ready for step 3 here. It's really the same idea as step 1, except we need the heat capacity of ice in this process, and we need to, of course, the final temperature is 268 and the initial temperature is 273. So we need to go out there and we need to look up the heat capacity of ice, and I'm going to scroll back up here because I've left a place for it in this document. So again, what I'm going to do is type up the heat capacity of ice because I've looked it up. And I'm just going to do CPI. I'm going to call it CPI as my heat capacity of ice. I'm going to use the quantity again. And it's 37.84 joules per Kelvin per mole. And this time I'm just going to use joules per the shorthand way, Kelvin mole. Put everything in the same quotation marks, close bracket, shift enter. There's my value. And I'm going to scroll down here to the next step. So here we have, in the next step, we're cooling the ice. So again, we're going to do the same thing. So I'm going to do escape, shift D, escape for delta. S3 for the third step, that's equal to the heat capacity of ice times the log. And you can do an asterisk here if it's times, but when Wolfram sees a space, it assumes there's a multiplication involved, so you don't necessarily have to do that. Sometimes it's better to put the asterisk because it's easier to understand, to follow, but in this case I'm not, I'm just doing the space. And now it's going to be T1, 268 divided by T2, which is 273. Close bracket, shift enter. There's my negative value of entropy, which again, because I am cooling, I expect the entropy to decrease in the cooling process. And so now finally, we're at the step where we can do the total entropy change in this situation. So I'm going to enter a section, and I haven't talked about this. I've already had the notebook separated into sections when we started out, but just to note, when you look at other styles of text, you'll see that there are just a whole bunch of options here that you can use. Sections is one. There are also shortcut keys for this. For example, if I hit for the Mac, a Command 4, for a Windows machine, Alt 4, it would also give me the sections. So I'm going to do total entropy. I'm just going to type that in. The other thing that's nice about sections is you divide into sections, there's a hierarchy of cells. And so all of the cells, for example, if I look at step 3, all of the cells that come below that before the next section are included. If I double click on that bracket, you see it collapses. So I can collapse my document. It makes it easier to read sometimes to do that. You can play around with that. That would work both in the cloud version and the desktop version of Mathematica. All right, so the total, I'm just going to go ahead and start typing. Escape, Shift D, Escape, S, we'll just call it delta S total, equals, and it's going to be 1, 2, and 3. If you get more sophisticated in your use of Mathematica, you can use indices and summations to so you don't have to use as many keystrokes, but this is a relatively simple situation here to do that. So escape, Shift D, S2 plus escape, Shift D, escape, S3, all right, and Shift Enter. And I've got the same problem I had before. Doggone it. Okay, so now we're ready to calculate the entropy change for the cooling of ice, and we have the formula. Let me back this off a little bit. We have the formula associated with that. We need the heat capacity of ice in order to do this. So I'm going to scroll back up here to this point and go ahead and enter that. We have to look that up, and it's going to be CPI is equal to, and then quantity, and the number is 37.84, and it's going to be joules per moles. I'll put that in parentheses. Moles times kelvins, close parentheses, bracket, Shift Enter, and there's my value. Okay. All right, so now we'll just scroll down here to do the calculation as I've set it up. I'll move this over a little bit. All right, and so we're just going to go ahead and start. So this is step 3. So I'm just going to go escape, Shift D, escape, S3 equals heat capacity of ice. All right, times log, and I don't have to use an asterisk here if I don't want to. A space, Wolfram will assume, is the same thing as multiplication. And T1, all right, because the final temperature is 268 divided by T2, close bracket, Shift Enter, there's my number. Okay, so now I've got a negative value for the cooling of ice, and that's expected because we are cooling. So when you cool something, you're actually removing the heat from that substance, and so therefore, because you're removing the heat, because you're making it a little bit more ordered, it's going to be decrease in entropy. It's going to be a negative entropy change. So now we're ready for the total. All right. So we're going to do a section. I'm going to do sections. I already had this notebook set up in sections to begin with, but in case you don't know how to do that, we're going to use another style of text. You can hit this plus sign here, other style of text, and I'm going to select section. I could also use Command 4 in the case of the Mac and Alt 4 in the case of a Windows machine to set up a different section. Wolfram has default font sizes and fonts and colors in the notebooks. When you first open it up, you can change all of that if you wish. You have a lot of freedom in changing styles, particularly in the desktop version. But for the most cases, the default is just fine. All right, so I'm just going to type total entropy here, and then hit the down arrow to get to the next cell. And let's go ahead and just type it in. All right, so escape, I'll call it total, equals, and just 1, 2, and 3. If you get more sophisticated in your use of Wolfram, you can learn how to use indices, and you can learn how to use summations to actually add these things together. But this is relatively easy. Just go ahead and type it this way. So escape, Shift D, S1 plus escape, Shift D, S2 plus escape, Shift D, escape, S3, and Shift Enter, and voila, there is my number. It's a negative entropy change. All right, and it's really dominating. If you look at the numbers here, the entropy change for the cooling is relatively small, as is for the heating. The heat capacity, didn't really discuss this, but the heat capacity of ice is a lot less than liquid, and that's typical because the particles in the crystal structure in the solid have fewer degrees of freedom, less ability to move, and so the heat capacity is lower in those circumstances. So you're generally going to find that the solid has a lower heat capacity than the liquid. And so so those are small numbers relative. The major contributor, of course, to the entropy change is the freezing process itself, and it's negative. So at this point, you should say, what's going on here? Because I thought this was spontaneous at -5 degrees. Why is it that we get a negative number? Is this a violation of the second law of thermodynamics? And the answer is no, it's not a violation of the second law, because what have we not considered yet? The second law is associated with the universe, or an isolated system. That in this case, we have just calculated the entropy change for the system, but not the surroundings. And as you might suspect, what's going on here is this is an exothermic process, all right? And so the heat that's being removed from the system is actually being dumped into the surroundings. So if the system is losing heat, the surroundings will be gaining heat, and the surroundings are going to have an increase in entropy. And the question is, does that increase in the entropy of the surroundings compensate for the negative entropy change in the system, so that the total entropy change for the universe is positive? And that's going to be the subject of our next video, where we're going to take a look at the entropy change for the surroundings and put everything together. We're going to stop here, and we'll come back to this in the next video.